Hello everyone, my name is Horace, and in this video we're going to be going through LeetCode number 70, climbing stairs. For this problem we have to climb a staircase, and there are n steps from the bottom to the top of the staircase. At every step in the staircase we can either climb 1 or 2 steps. We simply have to answer in how many distinct ways can we climb to the top of the staircase. So as always, let's go through an example. So suppose we have a staircase with 3 steps, so n is equal to 3. Then how many ways can we climb to the top of the staircase from the bottom of the staircase? Well, we could take 1 step at each step in the staircase, so we could go to step number 1, then step number 2, then step number 3. And this is one way to climb to the top of the staircase. Another way to climb to the top of the staircase is go 1 step to the first step, then take 2 steps to reach to the top of the staircase. But what if we take 2 steps at the beginning and then 1 step to reach to the top of the staircase? Well, now we have 3 distinct ways to reach to the top of the staircase. So the return value when n is equal to 3 is exactly 3. So to more clearly illustrate what we're doing, we can construct what is known as a decision tree. So let's use the example where n was equal to 3. Suppose we're starting at the ground level and we'll call that 0. Then from the 0th step, we can either take 1 step or 2 steps. So we can either go 1 step or 2 steps. And if we go 1 step, then we'll go to 1. And if we go 2 steps, then we'll go to 2. Then again, if we're on the first step, we can go 1 step or 2 steps. And if we go 1 step, we'll be at 2. And if we go 2 steps, we'll be at 3. Now we can see from this path, we have reached the top of the staircase at 3. So from this path, there's no point in going further. So we can simply stop taking decisions from this point forward. Now from the second step, we can take 1 step, and then that will lead us to the third step, which is also the top of the staircase. But if we take 2 steps from this, we'll be at the 4th step. Well, since n is equal to 3, we can't go past the 3rd step. So this path already is invalid. That means we can stop taking decisions at this point. Then we can complete the right side of the decision tree. Again, we have a 2. So we already have seen this before. If we take 1 step, then we'll go to the 3rd step. And again, we reach the top of the staircase. And we can't take 2 steps because we'll be at the 4th step, which is again not valid. So as we've seen previously, we have exactly 1, 2, and 3 ways to reach to the top of the staircase. So how can we transform this idea into code? Well, if you notice, this is exactly a recursive algorithm. Then what are the base cases that we need to consider when we're writing the algorithm? Well, one of the base cases is exactly when we reach the top of the staircase. So when we reach a value of n. In such a case, we want to return a value of 1 since we found a way to reach the top of the staircase. Or we exceed the top of the staircase by 1 and we go out of bounds. That's also a base case, so we just return at the end from there. Well, what is the time complexity for this algorithm? Well, for each level in the tree, we have 2 decisions. And in the worst case, we have a tree with n heights. So the time complexity, or the worst case time complexity, is big O of 2 to the power of n. And this is not the best because we're doing a lot of repeated work. So you can see this entire tree is found right here. And we've already solved this one. Is there a way we can use this tree over here to avoid additional cost in the algorithm? Well, yes, we can, and we can do that using something known as memoization. So what exactly is memoization? Well, for memoization, what we actually do is we keep a dictionary that stores the value evaluated with the root value. We know that 1 always evaluates to 1 since this is a base case. Also, we know that 2 evaluates to 2 as this is another base case. Remember that when we have one step, there's only one way to get to that step. And if we have 2 steps, then there are 2 ways to get to that step. So by definition, we need these base cases as their rules for traversing the staircase. Then we continue to add more and more evaluations in the staircase. And if it's not in the dictionary, we add it. But otherwise, we can simply look up the value, and that will reduce the cost to simply big O of n. And it will have a worst case space complexity of big O of n. That means once we evaluate the values of 3 and 4 and add them to the dictionary, then we won't have to reevaluate them again and again. And that will save us additional cost. And since the lookup in the dictionary is big O of 1 on average, then we can assume a total cost of big O of n since there are n steps that we need to traverse, and the worst case is just taking one step to the top of the staircase. Even though this solution seems good, we can actually reduce the worst case space complexity from big O of n to big O of 1 using a dynamic programming approach. So for the dynamic programming approach, we'll use a similar method to the recursion with memoization. As before, we'll keep a set of base cases, and we'll also keep an array instead of a dictionary to look up during the recursion. And as we discussed, for the base cases, we have when n is equal to 1, which will be 1, and when n is equal to 2, we have 2. We can also say that when n is equal to 0, we have 0, just for completeness. Then we can go ahead and construct the DP array. Now for the array, it's going to take n plus 1 space, since that's how many indices we have. So if we keep going with the n equals 3 example, we're going to have 4 places for the array. So we have 0, 1, 2, and 3. We already know the values of the first 3 indices from the base cases. So we know that 0 is 0, 1 is 1, and 2 is 2. For any following values after the base cases, we know it's just the 2 preceding values, since we can only get to the third value using the 1 before and the 2 before steps. So we can take 1 step, or we can take 2 steps to get to the current step. That means we can just take the value of the 2 steps before and the 1 step before and add them together. So 1 plus 2 is 3, and that is exactly the value that we need for this. And suppose if we had 4 steps, well, we just take the last 2 and we add them together to get the value of the current step, since we can only go from 1 step or 2 steps before. And in the end, we simply just want to return the nth index in the DP array. So if we had n equals 3, then we return DP with the index of 3. And if we had n equals 4, then we return the DP with the value 4. But this is still using big O of n space, since it's an array with n steps. But notice that we only need the 2 preceding values and not any of the values before that. So we can just keep pointers to the 2 values and increment them as we need. So if we had n equals 3, they would be at 1 and 2. And then we would move it over 1 and then return the second pointer. And if we had n equals 4, it would be moved over. We would again return the second pointer. And by doing this, we can minimize our space complexity to big O of 1. And also this sequence is known as the Fibonacci sequence. So really what we're doing is returning the n plus 1th Fibonacci number. And this is the formula for the nth term in the Fibonacci sequence. And we're returning the n plus 1th Fibonacci number. Well, if we had n is equal to 3, so 3 steps, then we would just return f4. And this is the 4th Fibonacci number, which is 3. And if we just use this formula, well, then we have a time complexity of big O of 1 and a space complexity of big O of 1. And this is the true optimal solution, but you wouldn't be expected to know that this is a Fibonacci sequence. The optimal solution is found using the dynamic programming approach. With that being said, we can go ahead and write the code for the 3 different solutions that were presented. Okay, we're on LeetCode and we can start writing the code for the recursion solution using memoization. So first we can declare a dictionary to keep track of the values that we've seen. Then we want to declare a helper function and we'll call it climb, and it will also take in n. Then we want to check if n is in memo. And if it is, we just want to return the value that's stored there. And this will be the O of 1 lookup time. Then we want to check the base cases. So if n is less than or equal to 2, then we would just return n. And then finally, we add it to the dictionary if it's not already. So memo with n is equal to climb with n minus 1 plus climb n minus 2. And these are the 1 step before and 2 step before. And we can just return memo with the value that we've just stored. Finally, we just return climb with n. And this is one of the solutions using the recursion and memoization. And you can see that code is accepted and we can check it out. This is running in O of n time with O of n space. The second solution is going to be using dynamic programming. So again, we use the base case n is less than or equal to 2, and if it is, we just return n. Then we want to keep the previous values, so previous 1 and previous 2 will be equal to 1 and 2, and these are the base cases. as we've discussed. Then we want to loop over from 3 to n plus 1, and then we want to update previous 1 and previous 2. So previous 1 will take the value of previous 2, and previous 2 will simply take previous 1 plus previous 2, and then we just return previous 2. And this should be the DP solution. And you can see that this is also accepted, and this code is running in big O of n time and has a space complexity of big O of 1. Finally, we have the Fibonacci sequence nth term solution. So this is just a constant time solution since we're only doing arithmetic. So we can take n and increment it by 1. Then we can establish the a term, which is going to be 1 plus 5, and then to square root it, we'll just raise it to 0.5 as the exponent, and then divide all of it by 2. Similarly, b is going to be the same term, except the addition is going to turn into subtraction. Then we can just return the integer value of a raised to n, subtract minus b raised to n, and then all of it is divided by the square roots of 5. So we'll just raise it to 1/2. And this is the constant time solution. So we can go ahead and submit it, and we'll see if it's accepted. You can see it's accepted, and this is the true optimal solution, O of 1, time and space complexity. So with that being said, hopefully this video helped you and you learned something, and I'll see you soon.